Hello, everyone. Welcome back. Today, I'm going to be talking about combinations. So, before we talked about permutations, permutations have to do with times when the order matters, right? The biggest difference, the most simple difference between combinations and permutations is that with permutations, the order does matter. With combinations, the order doesn't matter. So, combination is the number of combinations of R objects chosen from n distinct objects in no particular order, right? So, I'm going to give some examples. How would we know that we're using combinations and not permutations? How would we know that the order doesn't matter? Well, let's say, for example, that there's a 5-year-old who is taking some items on a vacation with him, and mother says he can only take 5 items out of his 10 that he owns. Well, in that case, it doesn't matter what order he chooses those 5 items in. If he decides to take the bat, the ball, the iPad, the TV, and the computer, well, doesn't matter what order he chose them in. He still chose all those items. I could put them in a different order, and at the end of the day, he still has the same items with him on the trip, so it doesn't matter. Another example is, let's say that we are choosing 5 people out of the 20 in the class to be part of a committee. Well, in that case, it doesn't matter what order we choose them in. If I chose, person A, person B, person C, person D, and person E, even if I chose them in a different order, there's still the 5 people who were chosen, right? Now, this one with the committee gets a little bit more complicated if there's certain positions on the committee, because then order does matter, right? Let's say there's a president, a vice president, a treasurer, a secretary, and I don't know, another member, something. Well, in that case, order does matter again, and it's permutations because we care who's the president, who's the vice president, who's the secretary, who's the treasurer. So even if it's the same 5 people, if the order is different, then it changes their positions, and so that's a different committee technically, right? And so, with in terms of the committee or group, it depends on are we distinguishing different characteristics, or is it just, oh well, who's in the group versus who is not in the group, right? In that case, would just be combinations because the order chosen wouldn't matter in those situations. So those are a couple examples where order really doesn't matter and we don't really care about the order. So let's see. Basically, here the NCR, or C with brackets N comma R, are the ways we can actually denote this, as it shows here. And it says there's this many ways of doing so. So let's review what's the difference between this and permutations. There's exactly the same equation, except here we divide by R factorial. Now, why would we divide by R factorial? Well, because the order doesn't matter. And so in this case, if it was just here, the order does matter. But if we divide by R factorial, right, we divide by, the number of ways all of these things can be swapped around, then of course we're going to get all the combinations where the order doesn't matter. Similarly to how back when a few lessons ago, actually now, when we did this permutation stuff and we said if there's identical things, we can swap we need to divide by them to swap things around and show that it's going to give the same thing. And in this case, we're swapping around everything. We're saying any of the 5 items, you know, or any of the 10 items, any of the R items, or it might be N. Let's see, what do they use? Yeah, any of the R items can be swapped around and it's the same combination. And so that's why this is just an extension of that, right? It's really just an extension of that if we think about it that way. Awesome. So now that we understand why this equation is what it is, let's talk about some examples. The first example says, how many combinations are there if 3 letters are chosen from A, B, C, D, and E if the order in which they are chosen does not matter? So we did a similar question to this with permutations of letters. In this case, the order we choose them in doesn't matter. So ABC is the same as BAC, which is the same as CBA, etc. So all 6 of those different permutations are only going to be counted as one combination because they all use the same 3 letters. So let's do that. 5C3 is equal to 5 factorial over 5 minus 3 factorial, 3 factorial. So that's 5 factorial over 2 factorial 3 factorial, which is 120 over, let's see, 2 times 6, which is 12. Yeah, 12. So therefore it's going to be 10, right? And this should be, you know, less by a factor of a sixth, right? It should only be, this number should only be 1/6 of the answer that we got when we took the permutations. Because what's the difference? We also divided by this 3 factorial to demonstrate that the different permutations, the different orders don't matter. And in fact, I do think we got 60 for the other one, and we're getting 10 now, and so that does make good sense. That is good and consistent, so that's good. Awesome. And one thing you might notice too, there's always going to be less. There's always going to be less combinations than there are permutations, right? Because in the permutations order matters. So we have to account for all the different orders. For combinations, it doesn't matter. So it's going to be a lesser number, right? Because for every combination, we have multiple permutations, if that makes sense. Okay. The second example says, from a standard deck of 52 cards, in how many ways could someone draw a 5-card hand? Well, of course, we're going to do the exact same thing. We're going to say, well, the possible numbers of hands would be 52 choose 2, or sorry, not 2, 5, because we're choosing 5 cards, which is equal to 52 factorial over 52 minus 5 factorial, 5 factorial, which is equal to 52 times 51 times 50 times 49 times 48 over, let's see, this would be 47 factorial, 47 factorial, so those cancel, over 5 factorial, which that's going to be a big number. Let me just calculate that in my calculator here. Let's see, 52 times 51 times 50 times 49 times 48, divide by 120, right? Because 5 factorial is 120. We are going to get 2,598,960. So that's a lot of hands, over 2.5 million different poker hands that we could get. So what are the odds we're really going to get a straight flush? Well, I guess there's 4 ways to get a straight flush, so 4 over this 2 million number. That's so not very likely. Or I guess the royal flush, sorry. Royal flush, not straight flush. There'd be more ways to do that. But anyway, we'll talk about that in the probability unit. That's not really a question for today, but basically there's over 2.5 million different poker hands we could possibly have. Very good. All right, let's do this next one. In Lotto 649, players must select 6 different integers between 1 and 49. 6 numbered balls are drawn, and the jackpot is awarded to a player who has selected all 6 numbers. Oh, it doesn't seem very likely you'll win, but okay. In order to guarantee a win, you need to purge the ticket for every possibility. How many tickets is this? Oh, okay, well, let's see. How many possible tickets is this? Well, 49 is the number of possible numbers, and we have to choose 6. We have to get all combinations of 6. However, they don't have to be in any particular order as long as the numbers on our card match the numbers that showed up on the television, or however you find out what the numbers were that the Lotto 649 people filled out, then we're good. So it's going to be 49 choose 6, which actually I guess that's why it's called 649, because there's 6 numbers and you have to get the correct 6 out of 49 numbers, so probably not very likely. So then we have 49 factorial over 49 minus 6 factorial, 6 factorial, which is going to be 49 times 48 times 47 times 46 times 45 times 44 times 43 factorial over 43 factorial, 6 factorial, so we can cancel those. Then let's plug this in. Okay, so that's going to be 13,983,000 1,816 tickets. So, I mean, I guess by the time you buy that many tickets, you guarantee your win, which is great. But, perhaps the win isn't doesn't pay you out as probably doesn't pay out as much money as you spent on all those 13 million tickets. So, yeah, so that's a lot of tickets. So in order to guarantee yourself a win, you've got to buy all 13,983,816 tickets. So that's big. That's a lot of tickets. That's for sure. And also, I guess you'd have to make sure that each ticket is unique. That you're buying. That you're really getting every single combination and not leaving any out or doubling any or things like that. Very good. Awesome. All right, let's do two more examples here. This next example says, let's see, what's it say? It says there are 20 players trying out for a soccer team consisting of 3 goalies, 10 defenders, and 7 forwards. In how many ways can a soccer team of 12 be chosen if the coach chooses 1 goalie, 6 defenders, and 5 forwards? Okay, so for this one, we actually have to apply the rule of multiplicity, which is that's something we learned in a previous day. In fact, on the very first day of Unit 2, Unit 2, Day 1, we learned about that, how we need to multiply the total combinations for the possible goalies times the total combinations for the number of defenders possible times the combinations for the forwards possible. Now is also a good time to mention that there is actually an NCR button on your calculator where all you must do is press in the first number and then NCR, then the second number, and then you will be able to hit enter and get the answers right away so you don't have to do it out. And that's what I'll be doing for this one. This one you do not have to do it out because we did 3 examples like that already. So how many ways is there? Well, let's see. There's three choose one ways to get a goalie, right? For how many goalies? Because we're choosing 1 goalie, there's 3 possible goalie tryout people available. For defenders, there are 10 defenders who would like the position, but we're only going to choose 6 of them, so 4 will not be chosen. And then 7 forwards, so we're going to do 7 forwards, and we're going to choose 5 of them, and so 2 of them will not be chosen. So let's plug that into our calculator. 3 choose 1 is just going to be 3. 10 choose 6 is going to be 210. And then 7 choose 5 is 21. So in total, there are 13,230 different possible teams. So there we have it. There's our answer. Okay. Let's do one more example here. A car dealership sells 7 different sedans, 5 trucks, and 3 sports cars. How many ways are there to select 10 vehicles for its showroom, including at least 1 of each type of vehicle, if the order is unimportant? So, what do we know? Let's think about that. Well, 1 of each must be chosen, for sure, right? And also, we know that 7 vehicles must be chosen, right? We must choose we must choose 7 other vehicles. Let's see, because we want to choose 10 vehicles in total, right? 10 vehicles total, but we must choose 1 of each. So already what we're going to do right off the bat here is we're going to choose 1 sedan, 1 truck, and 1 sports car. Okay? So that leaves us with what? That leaves us with 6 sedans are left after we chose 1 already because we had to. It said that we must select at least 1 of each type of car, so we did that already. 1 truck was already selected, so there's 4 trucks left since we chose 1 already, and there's only 2 sports cars left. So at this point, we've actually already met the requirement, right? We already met the requirement, so at this point, we want to know how many ways for the rest of the cars can we choose now that we already chose 1 of each. Well, the thing is, 6 sedans plus 2 trucks plus 2 sports cars is, let's see, is 12 rather. I was going to say it's 10, but no, it's 12. And we need to choose 7 more vehicles because we already chose 3 and we're choosing 10 vehicles total, right? And so therefore we want to do 12, choose 7, which if we plug that into our calculator, 12 and then the C button, the NCR button, and then 7, and then hit equals, we're going to get 792. And so therefore, there are 792 ways to select 10 vehicles for the showroom given these conditions. Awesome. Very good. Okay. All right, let's move on. Let's talk about problem solving with combinations. So, this one is reminding us again that a combination is the number of combinations of R objects chosen from n distinct objects with no particular order. So, that's just kind of reiterating what we've already done, just to remind us that that is indeed the case. Okay, so let's do some more examples on this one. Here it says, how many different sums of money can you make with 3 nickels, 4 dimes, and 5 quarters? Well, let's see. Well, how many different things can we do? Well, with nickels, we have 3 nickels, so either we could choose 0 nickels, 1, 2, or 3, right? So there's 4 different ways to choose the number of nickels, right? We could either choose 0, 1, 2, or 3 nickels. We can't choose more than 3 nickels because we only have 3. As for dimes, we could either choose no dimes, 1 dime, 2 dime, 3 dimes, or 4 dimes. So that's 5 ways. And then for quarters, there's 6, right? It could be 0, 1, 2, 3, 4, or 5 quarters. So that's 6 different things we can choose. So that is equal to 120 different sums. Now keep in mind one of those sums is just choosing nothing. And technically we could choose 0 nickels, 0 dimes, 0 quarters. Now personally, I think 120 is the correct answer because I do think it's possible to do a sum of money where we just don't choose any money. I think that is possible technically. However, there are some people who prefer to say, oh, well, there's 119 ways because they don't consider $0 as an option. They feel you must choose at least one coin somewhere. So either 120 would be correct, or also if you said 119, I will accept that as well. Because in that case, I'll just assume you decided to take off the 0 ones, right? The ones where there was nothing. Awesome. So yeah, so the answer here is that there are 120 different sums. And notice order didn't matter here. We didn't do anything to account for the order that we chose these things in, because if I choose 2 nickels, a dime, and a quarter, well, that's the same sum of money as if I'd chosen those in a different order. We're still getting the same money here. Yeah. Very good. And this question actually, this question also too, we're assuming, because the thing is, in real life, right, 2 nickels is the same as choosing a dime. That's something we didn't account for, right? And so this technically isn't quite right, but in terms of what was the question meaning for us to get, the question was meaning for us to do this. The question was not really meaning for us to recognize all the different things that technically would add up to the same sum. They should have said the different, how many different combinations of coins can you choose? So I'm actually going to change that because the question should really say something different given the answer they're looking for. Very good. All right, example 2 says, in how many ways can a fruit basket be made from 8 different single pieces of fruit? Well, here's the thing. Each fruit either is in the basket or it's not in the basket, right? So for fruit piece one, either the fruit is there or the fruit is not there, right? What about for the second type of fruit? Well, same thing. Either the fruit is there or the fruit is not there. So there's two options, either it's there or it isn't. Same with fruit three, right? All the way up until fruit number eight, right? And so therefore, the answer is 2 to the power of 8, which is 256. However, here's the thing. Um, if one of these combinations is a combination where there is no fruit, where we just said no to everything. And so that's not really a fruit basket. So in this specific case, I would actually argue that the better answer here is going to be 255, because we're subtracting off the option where there is not any fruit. Because if we don't put any fruit in our fruit basket, then is it really a fruit basket? Now that said, I will accept either answer because maybe in some people's minds you could have a fruit basket, like a basket that's meant for fruit that technically you chose not to put any in it or something like that. But I'd like to think of a fruit basket as a basket that does have at least some fruit in it, right? So I would personally say 255 is the correct answer, but would also be open to accepting either. I think 256 is close enough. Very good. All right, let's answer another one. This one says a basketball team consists of two centers, four guards, and six forwards. The team must send four team members to a rules conference. In how many ways could the team send four members to the conference if there are no restrictions? Okay, well, here's the thing there's 12 team members total, right? Two centers plus four guards plus six forwards. So that's 12 people. C4, right? We have 12 people and we're going to choose four of them, and the order doesn't matter, to go here. And so that is going to be, if we punch that in our calculator, 495 ways. B asks, how many combinations would there be if one center, one guard, and one forward must be chosen? Okay, so in this case, to choose the center, well, they're spelling it the American way. Either way, that doesn't matter. You can spell it however you'd like to. I'll be consistent or spell it the American way. Um, Center. So for centers, there's two different centers, right? So this would be two, choose one to find the number of centers. How about guards? There are four guards, and we must choose one of the guards to go, right? And then, because there are four of them. And then for forwards, there are six of them. So six, choose one. And then for the last person, it can be any of the remaining people, right? So we already chose three people, keep in mind. So there's 9 members who we can choose. And it doesn't matter if it's, a guard, a forward, or the other center, as long as we just choose anyone. So basically, this last one is just for anyone who is not already chosen, basically. Anyone who is not already chosen to go. So this is going to end up being just 2 times 4 times 6 times 9, which is 432. So therefore, there are 432 ways to choose. So you might notice, well, hey, that's almost as much as when there were no restrictions. And that's because in most of the cases when there were no restrictions, most of those did include at least one center, one guard, and one forward, right? There was very few of those that actually, excluded an entire group that only had guards and forwards, or only had centers and guards, or only had centers and forwards, or only had guards, or only had forwards, or things like that. That didn't really account for a lot of the possibilities anyway, and so this number is fairly close. Now, that said, if this number was actually greater than 495, then we would have a problem, because in the case that there's no restrictions and versus cases where there are restrictions, it's always going to be less. But in terms of how much less, it really depends how harsh the restriction was. If the restriction was more specific, was a very, very specific restriction that not a lot of the original combinations would have, then it would be a much smaller number. Good. All right, let's try this next one. It says at least two guards are chosen. Well, here's the thing. Um, at least 2 guards are chosen. So how many guards could possibly be chosen? Either 1, 2, 3, or 4 guards. So there's also a different way to do this. We can do this an indirect way and say, what are the total number of ways? And then subtract off the ways we don't like. So the ways in which 1 guard is chosen or no guards are chosen. So I'm going to show you what I mean. The total number of ways for at least 2 guards to be chosen is equal to the total number of ways to choose anything. So the total general ways minus the number of ways for no guards minus the number of ways for exactly 1 guard, right? Because we want to know what are all the ways in which we could do it for 2 guards or more. So if we subtract off the times when we have less than 2 guards, which are no guards and 1 guard, we can get there. So we already know the total number of ways is 495, and that's just because we already did that up here, right? 495, so we know that. How about how many ways, how many combinations are there of having no guards? Well, let's see. There are 4 guards, 2 centers, and 6 forwards. So that means we'd have to choose only people who are centers and forwards. There's 8 people who are centers and forwards together, right? 2 plus 6 is 8. So, and we would have to make it a team of only those people. So minus 8, choose 4 for no guards. Then we also must subtract off the scenario where there's exactly 1 guard. So that would be 4 guards, choose one of them. And then everybody else would have to not be a guard. So we'd have to choose from the pool of 8 people who are not guards, who are either forwards or centers, and choose 3 of them to, fill the remaining spots on this team. Right? Okay, very good. So now let's do it out. 495 minus, let's see, 70 minus 4 times 56, which is equal to what? That's 425 minus, let's see, what's 4 times 56? 224, which is 201. So as you can see, this one actually is a lot less than 495, right? This one is less than half of them because less than half of the original ways are ways where 2 guards are chosen. It is more likely, it's slightly more likely for either 1 or no guards to be chosen as opposed to there being 2 or more guards chosen. Good. Very good. Okay. And there's still one more problem, looks like, although one more problem with multiple parts, so perhaps 4 more problems in some people's eyes. Okay. Actually, you know what? We will do this. We will do this in the next class, okay? Because this class is already getting kind of long. So I will see everybody in the next class, and we're going to do one more example of this. And then we're also going to talk about the binomial theorem as well. So have a good day, everyone, and I will see you in the next class. Bye, everyone.